orbital model. Could you start your talk?
Okay. Okay, let me start. Yeah. Hello, everyone. Today I will introduce our recent work about ICO4 spin-orbital model on the triangular lattice. We found that its ground state can be considered as a quantum spin-orbital liquid state, which also breaks the translational symmetry. This work is collaborated with Dr. Hui Kejin from TU Munich, Professor Hong Haotu from TU Dresden, and Professor Yi Zhou from Institute of Physics, Chinese Academy of Science. For more details, please refer to our paper. In the first part of my talk, I will briefly introduce about quantum spin liquid, and I will also introduce tensor network methods which used in this work, and discuss why the tensor network related method is suitable for the study of quantum spin liquid. And in the second part of my talk, I will introduce ICO4 spin-orbital model on the triangular lattice in detail, and I will also introduce our parton midfield ansatz, which called stretching ansatz, to understand the physics of this model. And in a basic perspective, it's related to a non-trivial spin-on-forming surface. And I will also show our numerical results, which consistent our ansatz. In the last part of my talk, I will introduce the high-performance tensor library, which used in this work, which is called GrisQ. I will introduce the features in the current version, and I will also discuss the future development. Okay, let's move on to the first part. The quantum spin liquid is an interesting quantum phase of matter, where the dominant physical degree of freedom, the quantum spins are refused to form ordering or freeze to some random pattern like glassy state, or become something called well-span solid state, which break the translational symmetry. Even in the ground state at 0 temperature. The existence of quantum spin liquid usually means this system has a large entanglement and strong quantum fluctuation. So this feature gives us some hint about where we can find a quantum spin liquid. The first point is we need to enhance quantum fluctuation, but unfortunately for the pure spin system, we know that the spin 1/2 has the largest quantum fluctuation. Also, we can consider involve additional degrees of freedoms to the spins. For example, we can consider degenerate orbits to the spin system and enlarge the symmetry of the system to enhance the quantum fluctuation. The second one is we need to enhance geometric frustration. We know that for bipartite lattice, the 1/2 spin has some natural way to form orderings. So we need to consider some non-bipartite lattice, for example, like triangular lattice, Kagami lattice, and more fancier lattice. So the model, the triangular lattice ICO4 model enhanced both from these 2 points. So we can look forward that it may be something interesting happen in this model. And then I will introduce the tensor network related method used in this work. Here we use DMRG measure to calculate the ground state property. The DMRG measure, sometimes called versional MPS measure, and other various two-dimensional tensor network measures, which we didn't use in our work. These tensor network related measures can directly access to the ground state of a two-dimensional frustrated system. So for the study of quantum speed liquid, we need touch two dimension and ground state. So this unique feature lets these tensor network related measures are very powerful in the study of quantum speed liquid. Here I want to show the other examples. The first one is triangular-lattice Heisenberg model on the Kagami lattice, and the second one is half-field Haber model on the triangular lattice. We know that for these two models, tensor network related measures firstly provide very strong evidence about the existence of quantum speed liquid. Although its nature are still very controversial. And the other tensor network related measure we used here, which called MPO-MPS measured. I think that Huike has given a very nice introduction about this measure in his talk yesterday. Here I just briefly remind it for the self-consistency. We can use fermionic pattern construction method to study quantum speed liquid. The basic idea is we can use these fermionic pattern operators to reformulate original spin operators and then rewrite the Hamiltonian. And then we can treat the Hamiltonian in the mean field level. And here, the dm dagger is the creation operator of single particle orbits, which from by diagonalizing the mean field Hamiltonian, and then you can fill up the band, and finally you use this Goodweiler projector to project out no occupancy and double occupancy cases and obtain a wave function in the original spin Hilbert space, which called pattern ansatz. We can use this pattern ansatz to understand the physics of original correlative spin system. So the MPO-MPS method give a way to convert this kind of pattern ansatz to an MPS. Here we start from a vacuum, which is not nothing else but trivial MPS, and then you can create a particle using this creation operator. The key point of MPO-MPS method is that you can use an MPO to represent this creation operator. So this creation procedure can be considered as acting an MPO to an MPS. We know that the result is still an MPS. So we can repeat this procedure again and again until to the Fermi level. And finally, you can use this Goodweiler projector tensors to project to restore the physical Hilbert space and obtain the resulting MPS representation of the pattern ansatz. Of course, after each creation step, you can truncate the MPS if necessary. So the cumulative truncation error is the error of this algorithm. there are a lot of advantages if you can convert an part-time ansatz to an MPS. Here, I want to highlight one of them. That is, let study non-local properties like entanglement, entropy, and spectrum much easier using this MPS representation. Here is an example that this pattern ansatz provide chaos spin liquid state which has the same topological order with nu equals 1/2 Laughlin quantum Hall state. So we know that its ground state, its entanglement spectrum in the ground state will follow this kind of CFT countings. And this figure shows the related entanglement spectrum measured from the MPS representation of the pattern ansatz. You can see that nearly perfect counting is showing here. And then I will, let's go to the second part of my talk. Here, we consider the Kugel-Komsky spin-orbital model, which describe both spin degrees of freedom and orbital degrees of freedom. Here, these sigmas are polymatrices of the 1/2 spin, and tau are the polymatrices of two component degenerate orbits. When the spin channel and the orbital channel are equal weight coupled, the symmetry of the Hamiltonian enlarge from the SU2 cross SU2 to SU4 symmetry. You can write down the fundamental representation of the SU4 group using the polymatrices of spins and orbits. So in this case, this KK spin-orbital model is equivalent with SU4 Hashbar model. So we can use an SU4 fermionic pattern representation, which is a full flavor fermions to study this model. So you can use the pattern operators to reformulate these SU4 spin operators, and finally to restore the physical Hilbert space. We should keep single double occupancy constraint. Here, I want to emphasize that in this case, the particle number of patterns should be 1/4 field. Note the half-filling case in the SU2 case. Okay, we consider this model in the triangular lattice. There are some previous works related to this model. They all observe that in the narrow even weight cylinder, the system always breaks translational symmetry, which shows some stripes or even plated patterns. And this work also show that in the narrow in the odd weight narrow cylinders, there are some gapless features, for example, like spin gap close. And previous understanding of this model is consider this pattern construction, which called uniform pi flux model, and this is related band structure and Fermi surface. So in the two-dimensional, its physics can be considered as gapless spin liquid state with a spin on Fermi surface. So how to understand this dimerization in the narrow cylinders. So they argue that when in these narrow systems, some on-collapse interaction are relevant, so they can open a gap. But this issue is still not well settled. Maybe we need a more uniform description for both partially one dimension and two dimension. So let's back to our work. I will show our basic setup first. So we consider SO4 clicking model on the triangular lattice with fundamental representation. Here to maximum reduce, since we consider the one-dimensional tensor network measures, we use the cylinder geometry. To maximum reduce the finite size effect, we consider three kind of cylinder geometries. The first one is XC geometry, which is the same with in the previous works, and we also consider YC and another XC, which called AXC geometry. Since we know that the local Hilbert space of this model is large, so its DMRT calculations are very challenging. So here we keep the maximal we push our maximal kept bound dimension up to 18,000 to 20,000, and these figures show the relative ground state energy and the related truncation error with different bound dimension. In the width equals to 6 cylinders, and these are also our maximal cylinders we consider in our work. You can see that our DMRT calculations are well converged. Now, let me try to answer this question. To understand this strong dimerized feature, it's straightforward to consider that some translational symmetry breaking in the ansatz along this direction. So here we start from the uniform pi flux state and involve an extra parameter delta here to break the translational symmetry of the hopping along the x direction. When delta equals to 0, it restores to the uniform pi flux, and this is a related Fermi surface. But when delta not equals to 0, you can see that the topology of the Fermi surface changed. You can see that the Fermi surface forms some open orbits in the K-space. And these green lines are the momentum cut for a finite wedge cylinder. So you can see that if the cut doesn't touch Fermi surface, you can consider a gap phase along this direction. And then we check that if delta not equals to 0 ansatz is a better ansatz. A better ansatz means that the ansatz have a better variational energy and a better wave function overlap with the true ground state. So here, first we use the DMRT method to calculate the ground state of the system, and then we use MPO MPS method to convert ansatz with different delta to MPS, and then we can measure the energy of the MPS and its overlap with the DMRT wave function. This result measured from cylinder geometry, and this result measured from torus geometry. Here I use green lines to highlight the best value of delta. You can see that both for the cylinder and for the torus, the best answer is always delta not equals to 0, 1. Here for the torus geometry, there exists some extra subtleties. Since the torus doesn't break the reflection symmetry, so we need to consider something like a cat state, which is the equal with superposition of delta ansatz and minus delta ansatz. Then here I show the ground state correlations. Ground state correlations of RCO4 KK model, for the nearest neighbor RCO4 spin correlation, each pattern shows this strong stripe patterns, which is highly consistent with previous results. But except for the nearest neighbor correlation, we also consider a correlation along the x direction with large distance. Here you can see that not only for the even width cylinder, but also for the odd width cylinder, the spin correlation are always exponential decayed. And this figure shows in log linear plot. And you can also see that the correlation length in the odd width cylinder is about twice larger than in the even width cylinder, and the oscillation period in the odd width cylinder is also large than in the even width cylinder. And we also consider the correlation between these plaquettes. We consider the RCO4 singlet in this plaquette and measure the correlation between two plaquettes with distance. And you can see that its correlation is also very decay very fast. So we can consider that both for even width cylinder and for odd width cylinder, the system is always gapped in the x direction. And here I want to show more data about the odd width cylinders. And this figure shows the nearest neighbor RCO4 spin correlation distribution in odd width cylinders. You can see that even we push the bond dimension up to a very large number, its distribution is still not uniform. And you can see that maybe there exists some larger unit cell around this direction, and it's also consistent with the correlation results. Here, so we consider that for the odd width cylinders, there may exist a more complicated surface topology. Except for the ground state correlation, we can also measure the entanglement properties from the MPS. This figure shows the entanglement entropy measured in the cut between these columns, and you can see that not only for the even width cylinder, but also for the odd width cylinder, the entanglement entropy distribution are very flat, and actually they are not very sensitive with the ground dimension. So we can see that from the entanglement entropy measurement, they are also shows gap nature along the x direction, which is consistent with our correlation results. Yeah, here I want to emphasize this data here, and you can see that these data are measured in this weight bound here, for example, here and here. You can see that the entanglement entropy is very small in this weak bond. So we can consider that the entanglement between two strong straps is very weak. So the ground state of this system may be considered as something similar with an product state between these straps. Okay, so since the entanglement between these strong straps are very weak, so we can consider each of these straps as an isolated one-dimensional system. And we can even directly take out this period, this segment of MPS to consider as the state of this one-dimensional system. And so we can measure the entanglement in each of the bond, and here shows the entanglement results measured from both for the parton ansatz and for our DMRG calculation. And we use this standard formula to fit the central charge, and both for our ansatz and for the DMRG results, we obtain very consistent results that the central charge equals to 3. So that means each of this one-dimensional strap is critical, and this consistent with our Fermi surface picture. And central charge equals to 3 is also the same with the SCO4 level 1 CFT, which is actually the physics of one-dimensional SCO4 KK model. Okay, let's move on to the last part. Here I will introduce the high-performance tensor library used in our work. And actually, it is not a single library, but a collection of high-performance libraries written by C++. And it open sourced and LGPL license start from 2019. And it is created for quantum many-body physics purpose. So that means we pay more attention to the symmetric tensor. And since we want to calculate some challenging systems like Delft TJ and Haber model, we highly care about its performance. And the final goals of the GRISQ is become the bridge between the algorithms and the realistic models, and also become the bridge between the quantum many-body physics and high performance computing. Since we know that the hardware is faster and more complicated these days, so how to take advantage of this computing power? We need some connector. So for more details, you can visit our website and find us on the GitHub. And in the current version, the GRISQ include a low-level tensor computation library to process big tensor calculations, which called GRISQ tensor, and a higher-level MPS algorithm library to process the MPS-based algorithms, for example, like the MRG, which called GRISQ MPS2. We want to acknowledge all the related peoples and the projects. Okay, in the current version, for the GRISQ tensor, it provides a symmetric block sparse tensor objects. It supports an tensor with any dimension and with any number of abelian symmetries. And it also supports users to define their own quantum number. And it also supports a streamable I/O, which means you can convert a tensor to a standard C++ I/O stream. and it also provides the basic tensor manipulations like transpose, contraction, decomposition, linear combination, direct addition, etc. And for the GraceQ MPS2, it provides basic one-dimensional tensor network like MPS and MPO, and it also provides a uniform MPO generator, which can generate an exact MPO for Hamiltonian with any n-body interaction. And of course, it also provides a large-scale DMRG. And the GraceQ already has some applications in the study of quantum spin liquid and Dr. TJ and Harvard model. Here, I list a part of the applications. For the future development, to be honest, the GraceQ is still at its very early age, so you can read it from its version code. And since I recently joined in the RCCS, so the future development will focus on the tensor, especially symmetric tensor network in distributed memory systems. And we also consider scalable tensor network calculations. Okay, since the GraceQ is open source, so any contributions is highly welcome. Okay, finally, let me summarize the talk. I introduced the tensor network related measures used in our study, and I also discussed why a tensor network related measure is suitable to study quantum liquid. For the SU4 KK model and the triangular-lattice, we suggest that its ground state should consider as a strappy quantum spin-orbital liquid, both for quasi one-dimension and two-dimension. And we also propose a new part-on ansatz to understand it, and physics related to trivial topology of information. And finally, I introduce our high-performance tensor library at GraceQ. Okay, thanks for your attention.
Thank you for a nice talk.
Yeah.
Is there any question or comment? Yeah, I have a question about your tensor network library. Okay. Okuo-san have a question.
Okay. So I have about the user network. Right? So you said that you have already the implementation of PA. So there any plan about the PEPs or the other algorithms?
Oh no, in this case only support MPS and MPO. Yeah.
So but you have a basic tensor network library.
Yeah.
Is it possible to develop the PEPs algorithm based on that?
Yeah. Yes, you can develop them. Since actually we more pay attention to the performance of the lower tensor. So and actually in our study we didn't use the PEPs, for example, so we didn't implement them. But actually, you can use GraceQ tensor to implement this tensor network conveniently. Yeah.
Okay, thank you very much.
Is there other question, comments? Yeah, okay. I try to ask about your calculation result for SE4 Kugel-Komsky model. So you try to two methods, and one method, MPO method,
Yes.
is just ansatz for the wave function.
Yes. For example, you set up a specific data and obtain the pattern ansatz wave function, and then you can use MPO MPS method to convert this specific wave function to an MPS representation, and then you can do following steps.
Did you compare the variation energy and energy over this ansatz wave function? So, for example, you calculate the DMRG for this model, so you obtain the variation.
Yes, you can see that this dashed red line shows the energy from DMRG. Okay, here, and this curve show the energy from this pattern ansatz. So you can see that for at here it has minimal energy. It's the minimal energy with DMRG.
I see. Okay. And okay, is there other question? Okay, I have one more question. So, if we, okay, you want to say about this ansatz is very good to understand the result of DMRG calculation. So yes. Basically, the important physics is included in this ansatz wave functions.
So you mean this? You mean this pattern ansatz only suit for the maybe for the even weight cylinder? You mean?
Yeah. No. I want to say this is a very simple ansatz. So
yes.
But this variation energy is roughly very good compared with DMRG. So it means that this ansatz is very well to understand the ground state of SU4 Kugel-Komsky model.
Yes, we think so. Especially for even weight cylinder with this clear double unit cell picture. Yes.
Nice. Okay. Is there any question or comment? Okay. Thanks for your talk.
Okay, thank you.
Okuni-san, do you have
may I ask some question? So
of course.
I think that this kind of highly fluctuating system often exhibit some non-monotonous system size dependencies. And I want to ask how is in your computation about the system size dependence? Do you find any some non-monotonous, for example, LX dependence of the DMRG computation?
You mean, for example, for the correlation behavior? Here, here you can see that maybe you can see that this figure that for a wider cylinder, you can see that the correlation decays more faster than than a narrow one. So and also this correlation. So you can maybe you can consider that it's gapped along this direction for even for 2 dimension. Yeah.
So anyway, this behavior of this correlation function looks very smooth. So I mean that if you goes to bulk limit, you can maybe I think you can extrapolate the bulk limit from your computational result very easily.
Yeah.
Is this right?
Yeah. Sorry. Yeah. So you mean this? Yeah, this behavior is smooth. Yes, it's consistent with this size. So in our calculation, maybe there isn't any maybe singularities when you push the size. Yes.
Yes.